Okay, so now you think about, okay, so now filtering back to the idea of passing a signal, U, through a linear system. Now, the signal, as I said, we only had a finite number of inputs, like, so 1 to n, and it starts at 0. And now the question, how is the input, how do we kind of think about how the input operates on U of t? But everything remains the same. U of t through the discrete Fourier transform is just represented in terms of a finite number of sinusoid. Linear system operates on the sinusoid as eigenfunctions. So the outcome will be scaling of these sinusoids. And now we have that immediate representation of the discrete Fourier transform of the output from which we can recover the actual transform. Okay, so that's again, this gives us the power of thinking about how G acts on finite signals. Now, there will be errors here and there because the signal is not completed, and we have to kind of worry a little bit about that. So my claim is that if you put in a signal U of t over here, and as I said, t runs from 1 to n, and I'm interested in the output y of t also from t equals 1 to n, I claim that the discrete Fourier transform of y is directly related to G times the discrete Fourier transform of the input. G evaluated at e to the I omega, so the frequency response of the system, scaling the discrete Fourier transform of the input. But then there is a remainder over here that depends on the frequency, and that remainder is small, okay, it decays as square root of n for a strictly stable system. That there is a part that we have to accommodate, but that part goes away as n increases. So now the punchline in this is back to learning. Learning and estimation, I experiment with a system, whatever that system is. I try some commands, some intervention, I see some observations. I'm trying to learn what that system does. Now, in this time series world that we live in, I can do everything in terms of frequencies because I'm going to model, say, this particular system as a linear system. Okay, so the frequencies matter. So I'm saying to you, this is a very important formula over here. This whole formula, this whole thing is really important. Why? Because, let me erase this stuff so that we are not cluttered. Okay, so why is this important? It's important because this tells me how to relate the input that is finite in data to the output, which is also finite in data, through the transfer function or the frequency response of the system G. I can do this almost non-parametrically and rather easily, and that I can do. Now, the fact that this formula is correct needs proving. Okay? What we need to do is we need to actually show what is start from the definition of what the Fourier transform is of the output, of n values of the output. Remember that the output is the outcome of the convolution of inputs and output, and then manipulate this to see how all of these equations, this, and this, map the Fourier transform of the output to the Fourier transform, the discrete Fourier transform of the output to the Fourier transform of the input, or the discrete one to the discrete one as well, either one, right? And so I do this computation, which I will let you go through because it's only computation similar to what I've done before. And you see that, in fact, what you see here is this equation, yn minus g times un, okay, is a term that decays as a function of square root of n. That's all I care about, okay? So then I can write that the discrete Fourier transform, the Fourier transform of the output y is related to g times the Fourier transform of the input plus some error. But that error I can control as my data increases in size. Recap. A signal from 1 to n can be viewed in terms of sums of its fundamental frequencies. Now, linear system operating on this is nothing but acting on each one frequency at a time. And that produces our Fourier transform of the output. Very, very simple, very intuitive. Every frequency of the input appears in the output, scaled by the value of the transfer function. Now I have a representation of the output. Okay, so the error, what I have to worry about because I'm working with only finite signals, is that there's an error that disappears as the size of the signal increases, and that's in square root of n. This gives rise to what I consider the first non-parametric trivial estimation problem that I haven't even talked about estimation yet, but intuitively says, look, you made some observation of u of t and y of t for t equals 1 to n. You made those observations. You want to know what the system looks like. There's a quick and dirty method of doing it. Take the discrete Fourier transform of the signal you measured, of the output, the discrete Fourier transform of the signal you measured at the input, take the ratio, that's your estimate G tilde. You know that that's not getting you the exact G, but it gets you an approximate G that looks better and better as n increases. That's called a non-parametric estimate. And it has a lot of interesting properties and some bad properties that we will see a little bit later and may not follow this particular approach. Okay, but intuitively, that's what it is. I learned the value of the system at every frequency by looking at what happened to every frequency component of my inputs. Done. So this is a nice story about linear system, represented by convolution, really characterized by their frequencies. So by taking Fourier transforms of the inputs and outputs, we can actually do quick and dirty estimation of the amount of amplification a system is able to exert on each particular frequency. Doing the discrete Fourier transform is nice because if I start with a finite signal, discrete Fourier transform is a finite signal, everything is compatible, everything is simple. Perfect. So at this point now, we have learned enough to take us to the next level and say, so how do I start building randomness into the story? How do I build stochastic processes into the story? So I'm going to transition now from discussions of linear systems to discussions of stochastic processes, which will be in the continuation of this lecture.